It's your friendly math tutor, Miss C here, and today we are talking about scientific notation. Here are the big ideas. Our purpose with scientific notation is to make numbers more manageable. That means we're taking really big numbers or really small numbers and we're writing them in a very structured way so that we don't have a lot of zeros either at the end of a number or between the decimal and the start of non-zero numbers. All right, how do we do that? So we basically create a first number that has a value between 1 and 9.99999. So it has to be any number. It's going to be a decimal in many cases. It cannot be 10. It has to be a single digit number and it can be a decimal. And then we multiply that number by 10 to a power. Because remember, when you multiply by 10 or you divide by 10, you essentially are making the number 10 times bigger. In simple speak, that means that zeros, our number grows by a factor of 10, which means zeros are being added to our number. That's what multiplying by 10 does. All right, so let's get to it. So we're going to start looking at really large numbers to start with. And here's how I like to approach scientific notation. So when we're dealing with really big numbers, our first step is to make that first set of numbers very small. So you're going to notice in this example that we have 3,450,000. Well, the only non-zero numbers we have are 3, 4, and 5. I have to turn those numbers into a number between 1 and 9.9999, right? So the only option would be 3.45 because if I put my decimal place anywhere else, I would have a number that's bigger than 10, okay, or bigger than 9.99. So now I've just made this number that's pretty big. I've made it really small because it's 3.45. It's 10 times some number smaller. So now I need to figure out how do I make it bigger. So I know that if I raise 10 to any positive number, it's going to shift this decimal point repeatedly because 10 to any power adds 0. So think about this. 10 squared, that's 100. So I started with 1 0 and now I have 2. If I have 10 cubed, that adds 3 zeros. What that does, right, is it's moving the decimal point, right? That was right here. Or sorry, right here. 1, 2, 3. 1, 1, 2. Okay. So that's how that works. So that's why scientific notation works. So here's what I like to do. Our decimal point was placed right here. We need to count from where the decimal point was and count how many numbers or how many places the decimal point needs to shift. And we do that by counting all of these digits here. So we need to shift it 6, the decimal place needs to be shifted 6 spaces to the right. So if we raise 10 to the power of 6, that's what happens. 3.45 times 10 to the power of 6 gives us an equivalent number, which is 3,450,000. All right, this number is small. I'm highlighting all of my non-zero digits. Sometimes it's good to practice with small numbers, so it's really easy to tell if we did this right. So the way that I can write this as a number between 1 and 10 is by moving the decimal place between the 1 and the 2. Okay, that's right there. That means we essentially shifted our decimal place 3 units. So I'm going to multiply this by 10 to the power of 3. Be careful, sometimes students forget to multiply by 10 and they multiply by 3 only. That is incorrect because 1.234 times 3 is not the same thing as 1.234 times 10 to the third. All right, moving on, we have 105,300,000. This is a tricky one because I see my first zero here, but it's trapped between non-zeros. So we actually have to go all the way to the end of my first non-zero number. So I'm going to rewrite this as 1.053. You might be wondering, does it matter how many decimal places you have? No, it doesn't, because this is still a number between 1 and 10. Okay, so now we're going to multiply this by 10. Our decimal place would be right here. I'm going to show you a shortcut for counting spaces. So I know that I've got 3 here, I've got 3 here, so that's 6, and then I've got 2 more, that's 8. So that's another way of counting if you don't like drawing this little loopy thing there. Okay, so what you're going to notice when you're going from a large number to scientific notation, it's 10 to a positive power every single time. Because remember, you're making that number smaller when you write it as a decimal. So then you need to raise it to a positive power to move that decimal place back out. So remember, these numbers are all equivalent, right? 3,450,000 is equivalent to 3.45 times 10 to the sixth. 1,234 is equivalent to 1.234 times 10 to the third. Okay. All right. Now, the decimals are a little bit different, and we still follow the same premise. So we're looking for our first set of non-zero numbers, which is right here. And we start by writing this as a number between 1 and 10. So I'm going to make this 4.5. I'm still going to multiply it by 10, but I want you to notice something. 4.5 is significantly bigger than 0.000045. To make this number smaller, my exponent has to be negative. So remember, when we raise 10 to the power of a negative number, that essentially means that I'm dividing by 10 to some power. I'll show you in just a second. So we put our decimal place here. So we count backwards from here. So we counted 1, 2, 3, 4, 5. So this is 4.5 times 10 to the negative 5. So if you've studied exponents, you know that I could rewrite this like this. Okay, so 4.5 divided by 10 to the power of 5 creates a really small number. In fact, it creates this small number. Okay, so we're going to follow the same pattern here. So I'm highlighting my non-zero digits. So I need to turn this number into a decimal between 1 and 10, or 1 and 9.9999, because we can't make it 10. And I get 3.789 times 10. Now, my decimal place was right here. So I count from right here. 1, 2, 3. I made my very small number bigger, so it's to the negative 3 because I need to make it smaller again. All right, and this very last problem, I only have one non-zero digit, so that's 7. You could write this as 7.0 if you want, times 10 to the negative. Okay, so here's some times where people get tripped up. My decimal place is technically right here, because it's 7 point, you could think 7.0, okay? So I'm counting back 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 digits. So this is 7 times 10 to the negative 13th. Again, 7 is much bigger than this long decimal that has 7 at the end. That's why we're raising it to the negative power, because these two numbers have to equal each other. All right, so big differences on these, right, is that when we go from a small number, I'm going to say to scientific notation, we end up with 10 to a negative power every single time. Okay, the other difference that is important to note is that, and I guess this is not so much a difference, but same with a slight difference, is that we're always counting from where the decimal point is. But what you're going to notice is on big numbers, you almost always include all of the non-zero numbers in your count. Whereas with small numbers, you're going to notice that I'm not including, like in this one, I only counted the 4. In this one, I only counted the 3, and here I counted the 7. So that is also a difference. So the big takeaway here is you need to count from the decimal place every single time. If you found this video helpful, please like it so it shows up for other people in their feed. And if you want to see more math videos when they're posted, subscribe. Till next time, remember, you've got this.